Okay, and I didn't pick up my chalk, which I dropped just a second ago. Starting here, I understand that my field is going to be almost radial. So I'm going to draw a radial line here. But from the very start, say starting on this little circle, we are going to have some influence of this negative charge. And the further we get from this point, the less the ratio of the distance from this charge to the distance from this charge. Meaning, if we're out here, and that's actually probably off the screen as you can see it, if we're out here, well, we're about, a little more than a handspan from this charge. We're a little more than 2 handspans from this charge. So that the two fields out at this distance will be in a ratio maybe 1 to 5. In other words, the influence of the negative charge will be about 1/5 as great as the influence of the positive charge. And you can visualize what that would look like. Positive charge will give you a vector out this way. Negative charge will give you a vector back this way, not quite in the opposite direction to this one, but kind of close, which is going to shorten this vector and tilt it down a little bit. So as we move away from here, the field lines, and I'm not going to draw actual field vectors, I'm going to draw direction vectors. And maybe I ought to draw those in a different color, which is what I started to do. Okay, so my direction vectors for the field are going to be pretty much radial at this point, straight away from the positive charge. And maybe close to radial out here, but by the time we get out here, they're starting to deflect downward a bit. If we continue this, eventually, and I'm kind of exaggerating the rate at which this is going to occur, these lines are going to come down and become vertical right here. So we're going to have something that looks like this. We'll probably have to go a lot further, and I didn't get the shape of that. I don't think I did a very good job of that. Now, there are symmetries involved that you might want to think about to tell us that what happens down here, if we follow this line and follow these vectors along this line, is going to be a reflection of what happened up here. So that we're going to end up with field lines, with a curve that does this. It loops around. And the same thing is going to happen if we start in any direction. We're going to start out in a radial direction here, but we're going to get turned around. And then we're going to come down here, not sure how that's going to work the way I drew it, but, and I was looking at a horizontal line. I looked at the wrong one. It's at this line where this loop should become vertical. So I'm going to fudge a little correction here. Actually kind of a big correction. It's a little uncomfortable making that turn as rapidly as I did anyway, but okay, so we come down here. Here's where we become vertical. And then something very similar, kind of a reflection of this, occurs down here. not very well drawn. Now that little error got repeated up here, and it's a little more serious. This thing's not going to turn down at nearly the rate I depicted. So my pretty picture's not going to be as pretty as I wanted it to be. It's going to go more like this and down here. More like this. Okay, we go in this direction. And you should try sketching these yourself. You get something like this. It's not supposed to be a dotted line. Now if we start off in this direction, we get closer to this thing a lot more rapidly. So we're going to move away from the radial pretty quickly. Then we'll move down like so. That's going to be similar on the other side. So on the other side it's going to be all symmetric for what we did, so I'm going to try to draw it that way. Okay, so I'm going in the radial direction, but I'm turning kind of quickly. And becoming vertical here, and it's going to be closer and closer to radial. And then kind of in this direction. Didn't do a very good job of that. And here. And of course I'll have lines here, vertical lines. And I might as well. I did a pretty good job, bad job of that. I lost my symmetry, but we'll pretend I know what I'm doing. And we get something like this. Not hard to draw if you get the idea what the picture should look like. But if you're guided by the way these vectors behave at various points, you can develop a reasonable intuition for drawing these things. And I haven't drawn that many of them. And I'm not going to enter that in any beauty contest. Okay, so we see a bit of dipole then. If it's centered at the x-axis and I'm drawing that too low, I can see on the monitor, it's a pretty small monitor, big enough to see that I'm way too low there. Try again. Okay, I'll just draw one up about here. Okay, dipole oriented in the upward direction, centered at the origin. You're going to have field lines that start radial, turn, become vertical, and then come back. Those are shaped of these loops. And you can work out the shape. All you got to do is use any kind of an inverse square law. And if your analytic geometry is up to it, figure out what these shapes are. Kind of missed the axis there, didn't I? Okay. Kind of lopsided. But you kind of get the idea, kind of like almost a butterfly shape. We understand that as you move further and further from the dipole, the field strength is going to get smaller and smaller. Field strength here is only this big. The field strength out here is going to be much smaller, so small that I can't really draw it. So if you have field vectors along these field lines, they're going to be directed away from the positive charge toward the negative. And they're going to get smaller and smaller as you go away from the dipole. Now, that's kind of a heuristic. So that if the field is this big here, it'll be smaller here, smaller here. It'll be really tiny here, and here, and here. Then it'll be a little bigger here, a little bigger here, and somewhat bigger here. The arrows follow the field lines away in the direction from the positive charge and then toward the direction of the negative charge. The positives on top and the negatives on the bottom go from the positive to the negative, just like what you see here. I'll also comment that if you work out the field of a loop, X, Y, Z plane, and a loop centered at the origin, intersecting the X and the Y axes. And incidentally, down here, if you rotate this thing 360 degrees, these loops will make sort of an egg whisk, a three-dimensional shape that's pretty easy to visualize. That's a typical cross-section. If you slice it this way, it's the same cross-section, and so forth. And if you've had multivariable calculus, you understand how to rotate shapes. Okay, well, I'm not going to attempt to draw this in 3 dimensions, but within the XY plane, the field that you get from this is going to follow the same field lines and the vectors in the same proportion. Kind of losing my symmetry here. In other words, by measuring the field, you cannot detect whether the field is created by a current loop or by two charges, two opposite charges. And that's kind of a good thing, because for an electric field, this works just fine. For a magnetic field, there's no such thing as a positive or negative magnetic charge. Those charges can't be separated. All magnetic fields are created by dipoles of this nature. So this is the model for how you create magnetic fields. Wanted to be explicit about that. You know, my history, somehow I missed what a dipole field was, so I could do the math with dipole fields, but I never really knew what this dipole thing was or why it was important. Yeah, I can do the math, I can do the Maxwell's equations up to an extent. Never really knew what they were talking about, so I think it's kind of important to understand this distinction. You can do the symbols. If you don't know what the symbols mean, at least if you have my kind of approach, which I don't recommend anybody to emulate, you don't have a grasp. Okay? You do manipulations, you can solve equations, but you don't have a grasp. So you want to grasp this distinction. No distinction in the fields. There's an equivalence, but for magnetic fields, there's no such thing as this kind of a dipole, only the kind that's generated by a loop. I'll also mention that there's a right-hand rule for the direction of the dipole field. If the current loop, so here's a current loop, let's just say here's your loop, and the current's moving in one direction, put your fingers in the direction of that current around the loop, your thumb points in the direction of the dipole field, so that, again, your field might look like this. Looping around. From positive to the negative, where the positive is the direction given by the direction of the current loop.